Let's say we run an experiment to determine if a reaction is endo or exothermic. For our hypothetical reaction, A reacts with B to form C. And let's say this reaction takes place in aqueous solution in a beaker. We can define our system as the reactants and products that make up our chemical reaction, and everything else is part of the surroundings, for example, the water, and also the beaker the reaction is taking place in. Let's say we run the reaction and we put our hand on the beaker and we feel that the beaker is warm. If the beaker is warm, since the beaker is part of the surroundings, energy must have been transferred from the system to the surroundings. So heat flowed from the system to the surroundings. And that's an example of an exothermic reaction. So delta H is negative. We can determine the amount of energy that flowed from the system to the surroundings by looking at the energy profile for our hypothetical reaction. In an energy profile, potential energy is on the y-axis in kilojoules per mole, and reaction progress is on the x-axis. So as we move to the right on the x-axis, the reaction is occurring. Our reactants, which are A and B, have a certain amount of potential energy, so that's right here on our energy profile. So that part represents the energy of our reactants. Our reactants react together to form our product, which is C, and that's at the very end. So over here, this line represents the energy, the potential energy of our products. Notice how the potential energy of our reactants is higher than the potential energy of the products. So if we were to find the change in energy, that would be the final minus the initial, so the energy of the products minus the energy of the reactants. For this energy profile, the energy of the products is about 50 kilojoules per mole, and the potential energy of our reactants is at 100. So this would be 50 minus 100, which is equal to negative 50 kilojoules per mole. So on our energy profile, we could show delta E, which would be this difference right here. So that represents delta E. And the change in energy, delta E, is also equal to the change in the enthalpy, delta H, for this reaction. So we know that the change in enthalpy is equal to negative 50 kilojoules per mole. So let's go ahead and plug that in over here on the left. So by feeling the outside of the beaker, we knew that the reaction was exothermic. But the energy profile allowed us to figure out how much energy was transferred from the system to the surroundings. So for an energy profile, when the energy of the reactants is higher than the energy of the products, this is the energy profile for an exothermic reaction. Let's say we ran a similar reaction where A plus B turned into C, but this time when we felt the beaker felt cool to the touch. If that's the case, it's because energy was being transferred from the surroundings to the system. And since the surroundings was losing energy, that's why the beaker felt cool. So heat flowed from the surroundings to the system, and this occurs in an endothermic reaction. And the change in enthalpy delta H is positive for an endothermic process. When we look at the energy profile for an endothermic reaction, the energy of the reactants, so go ahead and write reactants in here, the energy of the reactants is lower than the energy of the products. So this time, if we find delta E, that would be the energy of our products minus the energy of our reactants. And the energy of our products is about 100 kilojoules per mole, and the energy of our reactants is about 50. So let's say it's 100 minus 50, which would be positive 50 kilojoules per mole. So on our diagram, if we represent delta E, that would be this difference here on the energy profile. And once again, delta E is equal to the change in the enthalpy, delta H, for the reaction. So delta H for this hypothetical reaction is positive 50 kilojoules per mole. Since delta H is positive, we know that energy was transferred from the surroundings to the system. And that's the reason why the products have a higher potential energy than the reactants in our energy diagram.